we are starting deformation of solids. Deformation of solids, right? All right. So when a pair of forces, right? When a pair of forces stretches, or squeezes, or twists. So deformation of solids, we're investigating what happens when you subject different materials to stress, right? So that's what we're investigating. So when a pair of forces stretches, squeezes, or twists a solid, material, right? Solid material. The material is deformed. We say the material is deformed. Right? So that's what we mean. So, deformation refers. So deformation. So this refers to the change or distortion. Of the shape and size of the material. So that's what deformation is. Is the change or distortion of the shape and size of the material. So if a pair of stretching forces applied at the ends of the material lengthens, right? So if we apply, like so a pair of forces applied at the ends of a material, it stretches. We know that we're stretching it, right? At the ends of a material lengthens or stretches, right? So we are lengthens, right? So, and then a pair of forces, that are squeezing. So if we're squeezing forces, that are squeezing, shortens. So if we're squeezing forces, they shorten. And then stretching forces lengthens, right? A pair of stretching. So I have to write stretching here. X. So and then stretching lengthens, so squeezing shortens, right? So the deformation that stretches is tensile. So we know that the deformation that stretches, so we stretching, so it stretches. So deformation that stretches is tensile, and then we know the deformation that squeezes. So the deformation that squeezes, right, is compressive. So these are compressive forces. Compressive, right? And that twists. So deformation that twists, they're shear. They're called shearing forces, right? So that's deformation of solid. Introduction to deformation of solids. Now I want to look at what is called stress. Right. So now I want to look at stress. Okay, just stress. Right. Right. So a wire, right? So a wire, right? So if you have a wire of length L, right, and cross-sectional area, So we have a wire of length L and cross-sectional area A, right, supporting a load. So you have a wire, right, supporting a load, right. So a wire is supporting a load, right, under tension, supporting a load under tension F, right. Remember, so the stress is given by, stress is equal to the force applied over cross-sectional area, cross-sectional area. So that's what gives us the stress. So the stress is equal to force over the cross-sectional area. So stress is equal to force over area. So the unit for stress, right? So the unit for stress is Newton, right? Per square meter. This is the Newton per square meter, which is just equal to pascals. So which is just equal to pascal, which means 1 Newton square meter, sorry. 1 Newton square meter is equal to 1 pascal, right? So 1 pascal, so the units are the same as the unit for pressure, since pressure is also G, force over area. Then let's look at strain. Strain, what is strain, right? So the strain in the length of that wire, right? The wire we're talking about. So the strain is given by, strain is equal to, right, extension over original length. So remember, if you load a wire, right, it's a fixed wire. If you load a fixed wire, which means it's going to stretch. We've applied stretching forces to the wire, so there's going to be an extension. So the strain is given by that extension over the original length of the wire. So strain is equal to extension over original length. So E is equal to extension over length, original length of the wire. So strain is a ratio. Remember, it's length over length, so it's a ratio, which means there's no units, right? So it has no units since it's a ratio, right? So since it's a ratio, so it has no units, right? So we've looked at stress, we've looked at strain. Now I want to look at what we call Young's modulus, right? So now I want to look at what we call Young's modulus. Okay, Young's modulus, right? So Young's modulus. Okay, so if we draw a graph, right? If we draw a graph of applied load against extension, right? Since load is related to stress, right? So if you draw a graph of applied load against extension, right? And a graph of stress against strain gives the same shape, right? So if we have a graph of stress against strain, right here, so we have something against, right? So stress in pascals, right? And then we have strain here, right? 0, 0, right? So we get something like this right here. So we get something like that. So if you draw a graph of stress against strain, so we obtain something like that, right? So the straight line region between the origin and P here, so the straight line region from here to here, it's a straight line, right? So it represents the proportionality, right? So that's proportionality, right? So it means in this region, stress is proportional to strain. Then P is the limit of proportionality, right? So P is the limit of proportionality. So from this, we see that stress is proportional to strain here. So from 0 to P, it's a straight line, it's supposed to be a straight line. So stress is proportional to strain, right? So therefore, stress is equal to K strain, right? So the constant of proportionality is what we call Young modulus. The constant of proportionality is E. So that's what we call the Young's modulus. The constant of proportionality is the Young's modulus. So stress is equal to E times strain, right? So that's what we mean. So meaning, so therefore, Young modulus is equal to stress over strain. So Young modulus is equal to stress over strain. Right? So now we want to derive the formula for Young's modulus. Right? So we know it's stress over strain, right? So it means E is equal to, what is stress? Stress is force over area. So this is divided by strain, which is extension over original length. So meaning Young modulus E is equal to FL over AE. Right? So that's what gives us the Young's modulus. So Young's modulus is a ratio, right? So the unit for Young's modulus is the same as the unit for stress, right? Since strain is a ratio, so it's also what? It's also pascals or Newton per square meter. So that's also the unit for stress and Young modulus is the same, right? So we know that unit for stress and Young modulus is the same, right? So now I want to look at an experiment to determine Young modulus. So there's an experiment that is done to determine Young modulus. Okay, so want to look at an experiment to determine Young modulus. So that's the setup, right, of the experiment. So we're considering consider two wires, right? Considering two wires, P, let's say P and Q, right? So this one will be Q, right? Which will be the test wire, right? Q is the test wire, and then P, this one will be the P, right? P will be the reference wire, All right. So, and then this is the vernier. So this is a vernier, right? So this is a vernier. So vernier, right? Vernier to measure. So this is a vernier to measure the extension. So we want to measure the extension of Q, sorry, to measure the extension of Q, right? So this will be a variable load. This will be a variable load, right? And then this will be a small fixed weight. So this will be a small fixed weight. So what is its function? Is to keep P taut. So we don't want to have any kinks, right? So to prevent any kinks, so it's keep P taut, right? So P has to be taut, right? So consider two wires P and Q, right? So which are approximately 2 meters, right? So they're approximately 2 meters each, right? So they're made from the same material. So made from same material, right? So they are made from the same material and supported by a common support, right? So they're supported by a common support. So the test wire Q is loaded, right? So we load the test wire Q, typically up to 100 newtons in 5 Newton steps, right? And the resulting extension is measured as a function of the applied load, right? So it's sort of like an experiment. So we are loading the test wire Q, right, up to 100 newtons in 5 Newton steps. So we're adding little by little weights, right, up to 100 newtons, right? So the wires are as long and thin in order to obtain as large an extension as possible. So that's a point to note. The wires are long and thin. So they are long and thin to obtain. So in order to obtain as large an extension as possible. So we want to get a large extension, right? All right. So the vernier arrangement, the purpose of the vernier arrangement is to measure the extension, right? So with accuracy. So we want accuracy. So that's why we use a vernier. So the wire must also be free of kinks, right? So that we get accurate results. So that's why we put a small fixed weight to keep P at taut so that we don't have any kinks, right? So if we plot a graph, right, like this, right? So we have a graph here. So of load, right? F, and then this is the extension, right? So if we plot a graph of extension against load, we get a straight line here. We have a straight line, right? So if we get a straight line and then we find the gradient, right? So we mean the gradient will be equal to E over F. So we've changed in Y over change in X. So the gradient will be equal to E over F, right? So going back to our defining equation for Young modulus, so we know that, okay, so we know that Young modulus E is equal to FL over AE, right? So which gives us, so if we were to split, we know that it's LA times F over E, right? So which gives us, so it's just we want to incorporate E over F. So simplifying, we were left with L over A E over F. Because if you were to put E over F here, which means it's 1 over, right? So here, so E, the Young modulus, is given by L over A times the gradient of an extension load graph. So the Young modulus is given by L over A times the gradient of the extension load graph. So the extension load graph, that gradient. Okay, so there are points you need to note. So the diameter and initial length of the wire are measured accurately, right, by a micrometer screw gauge, right? So we measure the diameter by a micrometer screw gauge, right? We use a micrometer screw gauge because we need accurate. So we measure the diameter of the wire, right, and the meter rule. So this means, right, the cross-sectional area A is equal to pi r squared, right? But r is equal to d over 2. So which means we have pi d squared over 4. So it means the area is pi d squared over 4. So substituting in this equation of Young modulus, so Young modulus E is equal to 4L over pi d squared, 4L over pi d squared, right? times gradient. So 4L over pi d squared times gradient. So that's what we get. So that's the experiment to determine the Young's modulus. Right. So we now want to look at graphs of stress strain of different materials. So we want to look at different materials, how they behave under stress. Now I want to look at the graphs of stress strain of different materials, right? So first of all, we're going to look at ductile materials. We're going to look at ductile materials. So we're going to look at ductile materials. So the graph, okay, it's like this. So here, right, for ductile materials, so strain, right, strain, and then we have stress in pascals. So it's stress strain graphs of different materials. So here it's a straight line, right? It's a straight line for ductile material. And then we have something like that, and then right, so and then here is B, which is called the UTS, the ultimate tensile stress, and then here is P, right? Here it's Y, and then we have a point here that's E, right? Okay, so 0, 0, right? So along the graph, right? So we want to explain from, let's say from O to P, right? From O to P, right? We know that it's a straight line. So this is a straight line, right? A straight line. From O to P, it's a straight line, right? Through the origin, which means if it's a straight line through the origin, which means stress is proportional to strain, right? Stress is proportional to strain from O to P, right? So the material retains to their original shape. So the material retains to original shape when the deforming forces are removed, right? When deforming forces are removed, right? So they return to their original shape and size and length when the deforming forces are removed, or when the stress is removed, right? So we say elastic deformation occurs. So we say elastic deformation occurs. So what is elastic deformation? It's when the material retains to its original shape and size when the deforming forces are removed. So that's what happens from O to P. That's why it's a straight line, right? So, and then up to E. So what happens up to E? So, so E is the elastic limit, right? So the elastic limit. So that's what we mean by the elastic limit. So the material will undergo elastic deformation, will undergo elastic deformation. So the material still undergoes elastic deformation, right? Which means they return to their original shape and length when the deforming forces are removed. Stress is proportional to strain, right? Now, when we're beyond E, if we continue loading the material beyond E, so the material no longer returns. So we've reached the elastic limit, right? We've crossed the elastic limit, so the material no longer retain its original dimensions. Right? When deforming forces are removed, when deforming forces are removed. So that's what we mean beyond E. So that's we've crossed the elastic limit, right? So the material no longer returns to its original dimensions. So we say the material has undergone plastic deformation. So we say the material has undergone plastic deformation, right? So at point Y, the yield point, right? So point Y is called the yield point here. So point Y is called the yield point. Sorry. So Y is called what? The yield point, right? So what does it mean? Which means the material extend with minimum stress. So the material extend with minimum stress. So we require little stress, right, for a considerable extension with the minimum stress, right? So that's what we mean. So point B, right? So at B, right? It's called the breaking point. It's called the breaking point. So point B is called the breaking point, right? Right. The material can no longer withstand any stress and breaks. So that's when the point material can no longer withstand any stress and breaks, right? So the material breaks, gives up. The material breaks. So this is called the ultimate tensile stress, right? Ultimate tensile strength. Sorry, ultimate tensile strength. Ultimate tensile strength. So UT is the ultimate tensile strength, right? It is the point where the force, like the force per unit area of the narrowest cross-section of the material is greatest, right? So the pressure, where the pressure is greatest, right? So examples of ductile materials. So what are the examples of ductile materials that we have? So for ductile materials, we have it's usually metals such as iron, we have steel, right? We have copper, right? So those are the examples of ductile. So ductile, what does ductile means? So ductile means it can be drawn into wires. Means it can be drawn into wires. That's what ductility means, right? It means it can be drawn into wires. Okay. So now we want to move on to brittle materials. Okay, B. So we're looking at brittle materials, right? So we did ductile materials. So we're now looking at brittle materials. Okay, brittle materials. So brittle materials, under stress, right? They undergo elastic deformation, right? Undergo elastic. So we know that they undergo elastic deformation, right? So, but what's unique about brittle materials? They undergo elastic deformation only, right? Right. But that deformation is very little, and often the material breaks, right? So often the material breaks. Often the material breaks. So that's what you need to know. So often the material breaks because the deformation is very little. So this is the graph here, stress strain graph with stress here, and then with strain, right? So we just reach the ultimate tensile stress, right? So the material breaks suddenly, right? So what you need to know is just it breaks suddenly, just breaks suddenly. But however, they can withstand large forces. So brittle materials can withstand large forces. Okay, they can withstand large forces. And what you need to know is that, so from this graph, which means they have no plastic deformation. It's only elastic. So they have no plastic deformation, right? So they have no plastic deformation. So examples with cast iron, and then we have glass, right? We have glass, and then we have concrete. So those are examples of brittle materials. Lastly, we want to look at polymeric materials. Let me just clear here. Right. Polymeric materials. So that's C. Polymeric. Right. What are these polymeric materials? Okay. So polymeric, let me just first by drawing the stress strain graph. Right. Strain. Right. So you've seen this graph before when we're talking about transformers. Nice. When we're talking about transformers, we did this graph. Here, right, exactly. Right, so this is loading, and this is unloading, right? So this is the loading, and then this is the unloading. So, so polymeric materials have neither elastic nor plastic deformation, right? They exhibit what we call hysteresis, right? Exhibit hysteresis. So they exhibit what we call hysteresis. Remember the hysteresis loop. So they exhibit hysteresis. So this region here between the loading and unloading, this is called the hysteresis loop, right? So that's what we mean. So the strain is greater during unloading than during loading. So that's what you need to know from this graph, right? The strain is greater during loading than during unloading than during loading, right? So that's what you need to know. So examples of polymeric materials, so include plastic rubber. So plastic rubber, and then we have rubber bands. So these are the examples of polymeric materials. Right, so we're done with materials. Now we want to look at fatigue. What we call fatigue, right? So what is fatigue? Fatigue, right? Okay, so fatigue. So is a deformation of a material. So this is deformation of a material, right? Due to cyclic applications. Due to cyclic, right? Due to cyclic application, right? And removal of stress, right? And removal of stress. Cyclic applications and removal of stress on part of the material, right? On part of material. So that's what fatigue is, right? So after we applying cyclic, right? So we do cyclic application, right? So the part, so the material suddenly breaks, right? When we reach the maximum stress, which is called ultimate tensile strength, right? When it also even have not been reached, so the material will suddenly break, right? So the phenomenon is called fatigue failure. So that's what happens, right? Fatigue failure occurs. Fatigue failure. So a fatigue failure, right? So that's what happens, right? So we have examples. Fatigue failure often occurs in the following examples. So these are examples where fatigue failure occurs, right? So remember when we want to break a wire, we bend it back and forth, right, until it breaks. So it heats up and then it breaks. So bending that wire back and forth. So we say bending part of a wire. So bending part of a thin steel wire, of a thin steel rod or wire, or wire, right, back and forth, back and forth, right, several times. So bending part of thin steel rod or wire back and forth several times. So you know that it suddenly breaks, right? So there is also second part, thermal fatigue of petrol, diesel and gas engines, right? Due to cyclic changes in temperature, right? Also, if thermal, remember when thermal fatigue, right? So if thermal fatigue, so thermal fatigue will mean when you have a car and you fill it up with petrol or diesel, then it is just packed, right? So there's high temperatures during the day, and then there's night, there's cold temperatures, and then the high temperatures, then during the night, the cold temperatures. So those are cyclic changes, right? So it's cold, hot, cold, hot, cold, hot, cold, hot. So the petrol undergoes thermal fatigue. So that's what we mean, right? And then we were looking at creep next. Last thing we want to look at is creep. So what is creep, right? So creep is a time-dependent deformation of a material at elevated temperatures and constant stress, right? So that's what we mean. It's a time-dependent, depends on time. So it's time-dependent, right? Dependent. So it's a time-dependent deformation. So it's a time-dependent deformation of a material at elevated temperatures and constant stress. So it's a time-dependent deformation, right? So it's a time-dependent deformation of a material at elevated. I don't know what's wrong with my pen. At elevated temperatures and constant stress, right? So the material will undergo permanent plastic deformation, right? So the material undergoes permanent plastic deformation. So it undergoes plastic deformation, right? So that's what happens in creep, right? Okay. So this happens in gas turbine engines, right? And ovens. Remember, so ovens they're exposed to high temperatures, right? Very high temperatures. So that's where creep occurs, right? So fatigue and creep, so they're similar, sort of like it's just the nature of